So we have discussed the equivalent circuit of the transformer. Now the different parameters, we have the shunt and series parameters of the equivalent circuit, right? These can be found by the open circuit and the short circuit test. So we will see how to conduct these tests. So first we will start with the OC test or the open circuit test. So the open circuit test, it is usually performed on the low voltage side. So we will discuss why that is later. For now we will see the connections. This is the transformer, this is the LV side and this is the HV side, let us say. Okay, the HV side is going to be open circuited. That is why it is called an open circuit test. Now on the LV side we are going to give a supply voltage where we are going to measure the current as well as the voltage and also the power. Okay, so this is how the wattmeter is represented, right? There will be a current coil which will be in series and a pressure coil which will be in parallel. So this is the wattmeter. Here we have the AC supply. Now what will be the current that will be drawn? The current drawn will be the no load or the excitation current. So if we take the equivalent circuit, it will be more clear what you are measuring, right? So what will be the equivalent circuit? You are going to take the exact equivalent circuit. So here we have the series parameters of the primary winding and here we have the shunt parameters. Okay. So wherever we connect, whether it is primary or secondary, whichever side is energized, that side will have the shunt parameters. So this if you take as R1 and this is X1, this will be what? XM and this is RC. Now what I0 is flowing into this and the supply voltage, let us say it is V1. Now since the current that is flowing is a load current, which is a very small value, right? It will be about 5 to 10% of the no load current. So the drop across this impedance, it is going to be negligible. So we are just going to ignore these two parameters when we are doing the open circuit test only. Okay, remember that only when you are doing the open circuit test you are going to ignore this because the drop across this is going to be very negligible. Now the supply voltage, it will be measured by the voltmeter. So we can get the supply voltage. And the no load current, it will be measured by the ammeter. So you can write down here voltmeter reading will be equal to the supply voltage more or less, right? So we will take it as V1. And what will be the ammeter reading? This is going to be the no load current I0. Then what about the wattmeter reading? The wattmeter reading, it is going to give you the no load losses. Okay, what are the no load losses? The hysteresis and eddy current loss, the core loss, right? So basically the power lost in this shunt parameters. Okay, the series parameters, they are very small, they are ignored under no load condition. Now let us see what are all the parameters that we can find out here. So these readings we will take as VOC, open circuit voltage, and this is IOC, this is POC, okay, just for the sake of representation. Now what all can we find here? We can find the input power factor angle. This is nothing but the phase difference between the supply voltage V1 and the no load current, right? So this is going to be cos theta naught. You can find as the power divided by voltage and current, right? Because VI cos theta will give you the real power. Now once you know the power factor, then you can easily find out the impedance, which is nothing but these shunt parameters, right? From the phasor diagram, if you remember, this is the voltage, then this will be the core loss current IC, and this is going to be the magnetizing current, and the no load current is going to be I naught. Now we found out this theta naught. So what will be IC? This is going to be I naught cos theta naught. So now we know I naught as well as cos theta naught. So you can get IC. Similarly, the magnetizing current Im, this is going to be I naught sine theta naught. Okay, so this also you can get. Then what will be the shunt parameters? Rc you can get as the voltage V1, which is nothing but the voltmeter reading, divided by IC, which is nothing but IOC cos theta naught. Okay, and similarly the reactance you are going to get as VOC divided by Im, which is IOC sin theta naught. So this is how you can get the shunt parameters from the open circuit test. Now a few points that you have to remember when it comes to performing the open circuit test. So the very first one is the open circuit test should be done at rated voltage. Okay, performed at rated voltage or at operated voltage, that means at whichever voltage the transformer is used for operation. So this is because the parameters they are going to change very slightly with respect to the voltage, but it will be better if you can just stick to the voltage at which we are normally operating that particular equipment. Okay, so at that condition, if we find out the shunt parameters, it is more than enough for us. So the open circuit test, it is performed at rated or the operating voltage. So the second, as I have already told you, it is performed on the LV side. Okay, preferred to perform OC test on LV side. So why is that? There are two reasons. The first is, if you consider a 200 volt by 2000, let us say 200 by 2000 volt. Okay, now we want to operate at rated condition, right? We want to perform the test at rated values. Now if you do the test on the HV side, then you have to supply 2000 volts, but if you are doing on the LV side, then 200 volt voltage supply is enough. Okay, so that is one reason. Lower voltage supply or voltage source is sufficient to get rated values, rated operating condition. Okay, this is one reason. And second reason, when you have a step up voltage transformer, right, LV to HV, this is the step up voltage transformer. Here what is happening to the current? The current is going to be stepped down. Okay, that means higher current is going to be present here at LV side, and here there is going to be lower current at HV side, because the kVA remains same, right? So that means if you are doing the OC test on the LV side, you are going to get a higher value of excitation current. Now we know that excitation current as it is a very small value. Okay, if you are doing on HV side, the excitation current is going to be still smaller, which will be difficult to measure. Okay, so higher magnitude of excitation current will be produced when LV side is energized. So this makes it easier to measure it. This makes it more convenient to measure the no load or the excitation current. Okay, and finally one last point, we have to use the wattmeter. It will have to be a low power factor wattmeter, right? Because the no load current power factor, it is going to be much small, right? Cos theta naught is very low. So these are a few points you have to remember when open circuit test is performed. Next we will discuss the short circuit test. So the open circuit test, it was used to measure the shunt parameters, and the short circuit test, it will measure the series parameters of the transformer, right? So first we will see how the connections are made. This is the primary and this is the secondary of the transformer. Okay. Now the short circuit test, the supply is given to the HV side. So we will discuss why that is later. This is the LV side. Okay. So here we have the ammeter, will measure the current, and here we have the voltmeter, and the wattmeter is going to be like this. Right. And here we have the AC supply. Now in the open circuit test we gave the rated voltage. Here we have to give rated current. Okay. And short circuit test, so the secondary side is going to be simply shorted. Now how will the equivalent circuit be? So the equivalent circuit, exact equivalent circuit, if you take, there is going to be a shunt branch here. Okay. And this is the series parameters of the secondary side. Okay, this is R1, X1, R2 dash. Here the parameters will be referred to the primary side, and this is X2 dash. Now what we do is we ignore the shunt branch. Okay, because the current that is flowing, the no load current here, in comparison to the rated current, it is going to be much small. Okay. So this we can take as ISC to represent the short circuit. The secondary is short circuited. Okay. So if you are ignoring the shunt branch, then you are just getting one single resistance, you can get one single reactance. What will this be? R1 plus R2 dash, and this is going to be X1 plus X2 dash, and this is shorted, right? So here we have the short circuit current ISC, and this voltage we can take as VSC. Okay, so basically the voltmeter reading is represented as VSC. This is equal to the applied voltage. Okay, and what about the ammeter reading? This is going to be nothing but the rated value of current. Rated current. Now what about the wattmeter reading? Here the wattmeter reading, it is going to give you the copper losses, PSC. This is going to be copper losses. So since we are performing the test at a very low voltage, the core losses are going to be very negligible. You can note down that point here. Okay, core losses will be negligible at low voltages. Now we will see how to get the series parameters. What will be the very first thing that you can get? You can get the power factor, cos theta SC. This will be what? The real power divided by the voltage into current. What else you can get? You can get the impedance, ZSC. This is going to simply be the magnitude of voltage divided by the magnitude of current, because we are only concerned with the magnitude here. We anyways have the power factor angle. So once you know power factor and the impedance, then you can easily find out the resistance and reactance. It is a series branch, right? So in series branch, the resistance is going to be equivalent resistance. It is going to be ZSC cos theta C, and the equivalent reactance, it is going to be XSC, which is equal to ZSC into sin theta SC. Okay, so this is how you will get the series parameters. So here also a few points that you have to remember while performing the SC test. The test should be performed at rated current condition. Okay, and the second point is, like I have already mentioned, this test is performed on HV side. Okay, HV side is energized. So note that this is only a preference. Okay, it is not like if you do on the LV side you will not get the result. Okay, but it is preferred to be done on HV side. So why is that? You can consider an example. Let us say a 200 by 2000 volt transformer is present. Okay, now whenever you are doing the short circuit test, what is going to happen, whether LV or HV, whatever is the case, the voltage that is required to drive the rated current, it is going to be much less as compared to the rated value. Okay, so the voltage is just going to be typically about 5% of rated voltage. This much voltage is enough because it is a short circuit test. There is no load, there is only the impedance of transformer, which itself is very low. So when impedance is low, to drive rated current we need just 5% of the rated voltage. Now say you are performing the test on the HV side, then what will be the required voltage? 5% of 2000, it is going to be 100 volt. Okay, 100 volt supply is required. And what about the current? You can consider the rating to be 100 kVA. Then 100 kVA by 2000, it is going to give you 50 amperes. This is the rated current value. Right? Now if you take the LV side, then 5% of 200 is going to be 10 volts supply. And what about the current? The current is now going to be 500 amperes. So you can see that on the LV side we need a supply which is giving a low voltage and a high current, which is more difficult to arrange. In comparison, on HV side you can see the voltage and the current, they are of moderate values. Okay, so this is why it is preferred to perform the short circuit test on the HV side. Now the next test that we have for analyzing the performance of a transformer, it is called as the Sumpner's, or it is also called as the back-to-back test. So in open circuit we only had the core losses, while in short circuit test we only had the copper losses. In Sumpner's test, what is going to happen, without actually loading the transformer, we are going to get both the core losses as well as the copper losses. Okay, so this will ensure that the temperature rise of the transformer is also studied. The temperature rise in presence of both the losses. So this can be achieved if we are using two identical transformers. Okay, so this is transformer 1 primary and this is the secondary, and the second transformer primary and secondary. So both of them, they should be identical. So now let's see how to give the connections. So this is the power line, let us say. Okay, so this is the positive polarity and this is the negative polarity. The other transformer also we connect in a similar manner. Now we have to measure the input, supply, power, voltage and current. So here we connect the voltmeter, which will measure the supply voltage, and here we have the ammeter and finally the wattmeter. Okay, this is how you represent the wattmeter, right? So this is the AC supply. So this is the connection on the primary side. Now what about the secondary side? On the secondary side you have to connect the transformers in series opposition. Okay, so this is the dot polarity. That means if positive terminal is polarity is here, then this will be energized positive polarity will be induced here. Similarly, if this is positive, here positive will be induced, right? So what we do is we connect this with this, and this positive polarities, they are both taken out and given to a low voltage supply. So here also we will be measuring the voltages and currents, right? So this is voltmeter, this is ammeter, and here we have the wattmeter, right? And this is connected to a low voltage AC supply. So now we will understand what is happening here. we will make use of the superposition theorem to understand. Okay, so this is the primary voltage AC supply, right? Now let us take the effect of only this voltage source while this voltage is switched off. That means it is shorted. Okay, so if this is shorted, then we will see how the secondaries are going to be. Only primary voltage is present, or you can say switched on. Then the secondary side, what will happen to the connections? This is the positive polarity, and here the second transformer, positive polarity is here. This is going to be connected like this. Okay, now these are both shorted now because the secondary side voltage is assumed to be switched off. That means shorted. So you can see here this positive and this positive terminal are shorted. So will there be any current that will be flowing? There will not be any current that will flow in the secondary of both the transformers. So you can write here, no current flows in secondary windings because they are in phase opposition. Okay. So indirectly what we are doing here, this is nothing but the open circuit test because the secondary current is not flowing. It is almost as if it is open circuited. Okay. Now if you take this voltmeter, ammeter, these readings to be V1, I1 and W1, let us say, then what will be V1? This is going to be equal to the rated voltage of the transformer. I1, it is going to be 2 times the no load current of each transformer. And what about the wattmeter? This is going to be 2 times the no load losses of each machine. No load or the core losses. So this is for the primary voltages. Now we will see what will happen, what is the effect of this secondary voltage. Okay. So if we have to find out the effect of the secondary voltage, then we have to, according to superposition, we have to consider the primary voltage is switched off. Switched off means it is giving 0 voltage. That means it is short circuited. We should consider that the source is short circuited. So now when the current is flowing through the secondary, now this is being energized, right? So this will become the primary. Now when current is flowing here, you can see that the voltage source here is short circuited. That means this and this will now be at the same potential, which is nothing but a short circuit test. So it is behaving like a similar to a short circuit test. You can mark the current direction. This is the short circuit current, right? Here if the current is flowing into the dot, then the current should flow out of the dot. Okay. So from here it is going into this. So here it is entering, which is the case, right? Because if this is entering, then here it should come out, right? That is what is happening. Here the current is coming in, it is going like this, and here it is going out. Okay. So if the current is going out here, then it should come here inside, right? Again from here the current will now be flowing like this. This is ISC, and again into this. So what is the current path? It will flow from here into the second transformer, and then again it will flow back into the first transformer. So you can consider only when secondary voltage is switched on. So remember, this is by superposition. Okay, that means the other source, it will be shorted. Okay. So what is going to happen? It is going to be like a short circuit test because the primaries will now be in short circuit condition because the voltage on primary side is switched off or shorted. Now what will be the meter readings? So you can see here, since it is a short circuit test, we need rated current. So this voltage will be equal to that value which will be able to drive the rated current. Now what will be the voltmeter reading? What will be the voltage value? So this will be equal to 2 times the voltage that will be required for each of the transformer. Why is this? Because you can see that the current is flowing like this and it is going out like this. So basically this and this, they are in series, and the voltmeter is across these series combinations of both the windings. Now what about the wattmeter? So the wattmeter will give twice the copper loss of each machine because it is supplying both the machines here. Okay, so you can write down the meter readings. The current will be equal to the rated current of each machine. Okay, now what about the voltage? This is equal to twice of the voltage across each machine, across each transformer to circulate rated current. And finally, the power is equal to 2 times the copper losses of each machine, full load copper losses of each machine. So you can see that you can get the same results as the OC and SC test in addition to the study of temperature rise. Okay, but one major disadvantage of the Sumpner's test is that the identical transformer availability will be difficult. Okay, one major disadvantage is that availability of identical transformers. So why is this a problem? Why the transformers should be exactly identical? Here in each of the meter readings, we are just assuming that the voltage, copper loss and core losses and everything, they are equal. So we are writing twice of that. Okay, so from here the meter readings, you can get the copper loss of each machine by just dividing by 2.